Hey, AP Statistics. We're going to talk about Chapter 10, and this is the intro to confidence intervals. So to start off, we're going to do a little bit of review and kind of build into how last chapter applies to what we're going to learn this chapter. So confidence intervals, to start off with, we're going to start, this is the section that starts what's called statistical inference, which means that we're providing methods for drawing conclusions about a population from sample data. So we're starting to not just find like the probability of like what we did last chapter, we're going to now base that information and draw a conclusion from that. Okay. So example 1, the admissions director at Big City University has an idea. He proposes using the IQ scores of current students as a marketing tool. The university agrees to provide him with enough funds to administer IQ tests to 50 students. So the director gives the IQ tests to a random sample of 50 of the university's 5,000 freshmen. The mean IQ score for the sample is 112. What can the director say about the mean score of the population of all 5,000 freshmen? And suppose we know that the population standard deviation is 15. Okay, so this is an important thing. We're going to talk about standard deviations throughout this chapter. So this is the population standard deviation. And we're going to have a couple sections in this chapter. But basically what we're trying to estimate then is the mean score for all freshmen on their IQ test versus just the information we have is of the sample of the 50 university students. Okay, so remember from last chapter, what does it mean to be an unbiased estimator? What does that give us in this problem? Okay, so definition of an unbiased estimator is that the mean of the sampling distribution of x bar, where is that going to be? It's going to be the same as mu. Okay, the population mean. In this particular problem, do we know what the population mean is? We do not. Okay, so this is unknown. That's the whole point of this chapter, is that's what we're going to try to estimate. What's the standard deviation of the sampling distribution of x bar? So this is again straight from last chapter. Standard deviation divided by square root of n. So the standard deviation they gave us is 15. Divide by square root of 50. So we calculate that, we're going to get 2.12. Okay, what does the shape of the sampling distribution of x bar look like? And how do we know? Okay, that's again straight from last chapter. So we have a sampling distribution for the means. How do we know if it's normal? We have two options. Either the population is normal, or we can use central limit theorem, and n has to be large. So here, we don't even know what the population mean is, so we definitely don't know what the population shape is. So we don't know that, but can we use central limit theorem? Yes, we have a random sample of 50. So we can say the shape of the sampling distribution of x bar will be approximately normal since n is greater than 30 by the central limit theorem. Okay, so now we know that the sampling distribution, oops, sorry, dropping stuff. Sampling distribution of x bar is approximately normal. We can apply the empirical rule, and so do you remember what the empirical rule stated? You know, it's approximately normal, so one standard deviation away would be 68% of our data. Two standard deviations away would be 95%. So we want to know how far away is the middle 95% of our data. Okay, so we're going to find that problem, or sorry, we're going to find that for this problem. Okay, so the middle 95%, oops, is 2 standard deviations away. And I'm saying away because we're going both directions. So in this problem, the standard deviation of x bar is 2.12. And we're going 2 standard deviations away. Okay, so part E kind of continues. Find what 2 standard deviations above and below the mean is. So 2 standard deviations, we're going to take 2 and times by 2.12 to figure out how far above and how far below. So we get 4.24 is 2 standard deviations above and 2 standard deviations below. So how we find that, we're going to take, we're going to go above and below the sample mean. Okay, so we're going to take x bar plus or minus our 2 standard deviations away. Okay, 2 times the standard deviation. So our x bar that we were given in this problem is 112. So 112 plus or minus 4.24. So we're going to subtract 4.24, and we're going to add on 4.24. Okay, so we're going to get 2 values. So 107.76 and 116.24. Okay, so this is kind of using our estimate to find where we think the population mean might be somewhere in that interval, in that boundary. Okay, and how we're going to write this is with parentheses around it. So it's important to note there are 2 possibilities for the basis of our confidence. Okay, either the interval contains the true mean mu's in there, or our simple random sample was one of the few samples for which x bar is not within 2 standard deviations, so that 4.2 points of the true mean mu. Okay, only 5% of the samples give such an inaccurate result, that we get an x bar that's so far away that when we use it for a confidence interval that we don't capture mu. Okay. Thing to note, the parameter mu does not change. Okay, the population mean doesn't change. We don't know what it is, but it doesn't vary. It's unknown. But what changes are the sample mean x bar, and then the resulting confidence interval. Okay, put a big fat star next to this. This we're going to come back to a lot. Same with the last point too, that's important. But mu doesn't change, okay? We don't know what it is, but it stays the same. Our sample means are what are going to vary and bounce around. Okay, so for the above example, our confidence interval was x bar plus or minus 4.2. It's really 4.24. Sorry, I don't know why I wrote that. It's called a 95% confidence interval. Okay, because we went 2 standard deviations away, so that's 95%. Confidence interval is 95% in this case, and it can change. We'll see different values. The general form of a confidence interval is going to be our estimate plus or minus the margin of error. Okay, so there's one thing I really want to show you. Okay, so I want to show you this website. It's kind of simulating what's happening with a confidence interval. So I input the values that we have from the last problem. So our mean, our sample mean, I put as population mean. So we're going to say it's 112. Standard deviation is 15. We are taking sample sizes of 50. And so what happens is we got a sample mean over here, but when we did the confidence interval, it's green because mu was in that interval. Okay, so if I do another sample, okay, the little dot moved because it's simulating a different sample was taken, and the confidence interval, it's green because it's capturing mu. Okay, so I can do this. Oh, and here we got one that's red. What this represents is that dot is far enough away, the sample means far enough away, that when we created a confidence interval, it did not capture the population mean. Okay, so this was one of the, we're going to look in the long run, it should only be about 5% of the time this happens. So I'm going to do this for 100, like we're going to do this 100 times. Okay, so we can see it. Okay, so here most of them you can see are green, which means they captured the population mean. There's a few that are red, okay, and that means that like 3 of them here did not capture the population mean. Okay, what I want you to notice also is that this 112 is staying the same. what you see are these little dots that move back and forth, back and forth. The sample means are all over the place. That is the key to this chapter. The sample mean changes. The population mean does not. Okay, it stays stationary. Sometimes our confidence intervals will contain mu, sometimes they won't. So if I do this like for some more, if I change this to 200 samples. So you can see there's a few more like red ones that pop up. Still, most of them are green. Over here on the right, you can see there's 192 that were green out of the 200. So right now, we have 96% of the samples captured the population mean. So when we say it's a 95% confidence interval, we're saying that in the long run, if we did this infinitely many times, 95% of the time, our confidence intervals should capture population mean mu. Okay. Oops. All right, back to the notes. So we're going to break up the confidence intervals for means into two parts. The first part is when the population standard deviation is known. Okay. This is called a Z confidence interval. In this case, this is actually really unrealistic because the whole point of a confidence interval is to estimate the population mean. Well, it seems kind of weird that we don't know the population mean, but we do know the standard deviation. So it's kind of a funny thing, but this is what we're going to talk about. Okay. So conditions for constructing a confidence interval for a mean. The data must come from a simple random sample from the population of interest. Okay. The sampling distribution of X bar is approximately normal. Okay, and just like we saw last chapter, we have two ways to get our normal assumption. First is that it's given that the population is normal. So therefore, our sampling distribution of X bar will be normal. And this is for any sample size, any size n. Okay, small or large, it'll be normal. Or the second way is if we don't know the population's normal, if our n is greater than 30, the sampling distribution of X bar is approximately normal by the CLT. The other big condition for doing the Z confidence interval is that the population standard deviation is known. Okay, so that's like why we're doing this. We're going to have to differentiate between this method and a different method. So this is what differentiates it. Okay, common error on the AP test is not checking the conditions before you find the confidence interval, even if you were not told to do so. Big deal there. Okay, make sure we're always checking conditions. Okay, so your formula for confidence interval is this: X bar plus or minus Z star, which we'll talk about what that means. Okay, but everything else you should recognize. X bar, standard deviation over square root of n. Okay, where X bar is the sample mean, sigma is the population standard deviation, n is the sample size, and Z star is what's called the critical value. A couple more vocabulary words for you, and then we'll talk about what Z star is. So the margin of error is in the confidence interval. It's the whole part that you plus or minus. Okay, that whole Z star standard deviation over square root of n. What's called the standard error is just the standard deviation divided by square root of n. You're estimating the standard deviation, but there will be some error involved because we're estimating it. Okay, so vocabulary here: margin of error versus standard error. Sorry, those are great multiple choice questions. So you got to make sure you know the difference between them. Okay, so the critical value Z star is the area under the curve for the middle percent. Key thing here: the middle percent. So, for example, the middle 95%, and here's this like little formula that I will show you how that works, okay? We're going to skip a couple because they're not really that helpful. Okay. So we're going to do 90%. We see that confidence interval a bit. So we're going to do 90%. Sorry, so we're just going to skip over this for a while. And so what this is saying is if we have a normal curve, we want the middle 90%. Okay, confidence interval is looking for the middle 90%. So when we draw this, we're trying to figure this out. How much then data do we have left over? Well, this is the middle 90%. We have 10% left over. And since it's the middle, it means it's split between two sides. So we have 5% on each side so that it all adds up to 100%. Okay. Z, we're going to go and try to find kind of like a Z-score. So if we already know the percent, we're not doing normal CDF, we're doing inverse norm. Okay. And so these are going to be, we want to know what these Z-scores are. Okay. They're symmetric. They're the same distance from the mean. So we're going to either do inverse norm. The lower one is 0.05. Okay, so go ahead and do that in your calculator. So you should get negative 1.645. And if you do the higher side, what's the percent all the way to the left of this value? It's the middle 90 plus that left 5%, so 0.95. And this is, again, it's symmetric, so it should be positive 1.645. Z star is always positive, so this is going to be what Z star equals, 1.645. Okay. So let's try a couple more. These are the most common ones to see. Okay, so 95, oof, that's a really ugly curve. Okay, 95%, we're talking about the middle 95%. Again, so you think about what's on this each side. There's 5% left over, and we split it between two sides. So this is 2.5%, 2.5%. Okay, so we're doing inverse norm. You can either just remember to do it for that little tail, so 0.025, and then make it positive, or you can do inverse norm of 0.975, because it's everything to the left. Okay, so either this value or this value. Okay, so go ahead and do inverse norm of whichever one you want. Z star, though, is just always positive. Okay, so you should get 1.96, which that's what Z star equals. The last one is 99%, so almost everything. There's 1% left over, so this is only 0.5% and 0.5%. So careful with the decimal places. This is either inverse norm of 0.005 or inverse norm 0.995. Okay, so go ahead and calculate that. And so you should get 2.576. And again, Z star only equals the positive. Okay, so on to example 3. Okay. Cosmic radiation levels rise with increasing altitude, prompting researchers to consider how pilots and flight crew members might be affected by increased exposure to cosmic radiation. A paper in Space Medicine and Medical Engineering in 2002 reported a mean annual cosmic radiation dose of 219, whatever these units are, for a sample of flight personnel on this airline. Suppose this mean was based on a random sample of 100 flight crew members, and let mu denote the true mean annual cosmic radiation exposure for this flight crew member. Okay, this airline's flight crew members. Suppose that the population standard deviation is 35. This is usually not known if the population mean is not known, but that's what we're going to solve for right now. And then we want to calculate a 95% confidence interval. Okay, so there's a few things that we want to make note of that we know. Okay, It reported a mean annual cosmic radiation dose of 219 for a sample of this flight personnel. So because it's based on this sample, that's our X bar. Okay. We also says that it's suppose there's a random sample of 100 flight crew members. Important to note. And we also have that the population standard deviation is 35, whatever these units are. Okay. They also tell us what mu is, the true mean annual cosmic radiation exposure for this airline's flight crew members. They're going to calculate a 95% confidence interval. So first off, okay, this is what you are going to have to be able to do. Draw sort of an arrow. Okay, identify the parameter of interest. Are we talking about a mean or a proportion problem? Definitely a mean. Okay, we have mean and standard deviation. So we're going to define what mu is. Mu is the true mean annual, Okay, the true mean, and it says it right here in this sentence right here. The true mean annual cosmic radiation exposure, and it's still for this particular airline. Our sample is just from this airline's flight crew members, not all airlines. So we want to be able to know what our results can extend to. So here we're not talking about other airlines like United and Southwest and all these other kind of airlines. We're just talking about this specific airline. Okay, so check our conditions. The first one is that the mean is based off a simple random sample of flight crew members. We were told that, so we've got that one. Okay, random sample of 100 flight crew members. Okay. The second condition is normality. Okay, so we either know that the population is normal, or, since in this case we don't know that, we have that central limit theorem. So here we can say the sampling distribution of X bar is approximately normal. Okay, that's approximate. Since n is greater than 30 by the central limit theorem. Okay, so far this really hasn't been anything new. The new part is the 95% confidence interval. So your formula for this is X bar plus or minus, we have our new Z star, standard deviation divided by square root of n. Okay, so let's plug in the pieces we know. We know X bar, they gave that to us, it's 219. Plus or minus, we don't know the Z star yet, we're going to figure it out. And we have the standard deviation, total is 35, divided by square root of n, which is 100. Okay, so Z star, you can either flip back to your notes and figure out what it was. On the quiz and the test, though, I'm going to have you actually show your work for this. So what I would want you to do is something like this, the middle 95%. You're going to say you're going to do inverse norm. Again, you can just do this this left tail, okay, which would be 0.025. And then you can write Z star equals, so go ahead and do that. You should get 1.96. Okay. So in your calculator, go ahead and do this right side is I want you to figure out, that's called the margin of error. So whenever you're solving these, you're always going to write the mean plus or minus, figure out this whole right side calculated together so that you get credit for showing the margin of error. So when you multiply 1.96 times 35 divided by square root of 100, you should get 6.86. Okay, and then you're going to add and subtract that on to 219, so you're going to get two numbers. You always write the lower one on the left, so we subtracted, so 212.14. And then you do the upper one, 225.86. The big thing to this chapter is also being able to interpret your results. We don't just find the confidence interval. We're going to write it in a sentence. And this sentence is kind of like a formula. I'm going to write it and we'll kind of go over this a lot and we'll talk about it a lot. Okay. So you can say, I am 95% confident that the true mean cosmic radiation exposure for this airline's flight crew members is between our two values. So 212.14, and I'm going to use the units. 225.86. Okay, so there's a couple pieces to this that you really need to have. Your confidence level. We have that we're talking about the true mean. This is the definition of the mean we're talking about, just like what we labeled above. Okay, this is where this comes from. Up here, just our definition of mu is between, and then that's just our confidence interval with units. Okay, so we're going to do example 4 in class. Thank you guys so much for tuning in. We'll talk soon.